The universe has a hidden flaw in its design. Picture space and time not as a rigid stage, but as a living, breathing fabric. Now imagine that fabric developing strange dents, mysterious tears, and inexplicable wrinkles. These are space-time anomalies, real cosmic glitches where the established rules of physics simply break down. Today, we are going on a journey through 25 of the most baffling ones. By the end, you will see the cosmos not as a settled fact, but as a collection of profound, unresolved puzzles. We will explore why distant galaxies are fleeing toward an unseen horror, and what secret caused a star to dim in impossible ways. What does it say about reality that our best maps of creation show a preferred axis, a shocking fingerprint of something ancient and strange lurking in the data? This is a voyage to the edges of our understanding, where every answer reveals a deeper question. Are you ready to question everything you think you know about how the universe works? Our first stop is a quiet mystery that unfolded in the deep silence between the stars. For decades, the twin Pioneer 10 and Pioneer 11 spacecraft sailed outward from our solar system, robotic envoys on a one-way trip into the cosmic dark. Yet as they journeyed, tracking their precise positions revealed something deeply unsettling. Both probes were slowing down just a little bit more than anyone had predicted. This tiny, persistent deceleration became known as the Pioneer anomaly. It was a whisper from the void, a force so faint it was like a single snowflake resting on the hood of a car, yet it defied every explanation. Mission scientists became cosmic detectives, ruling out suspects one by one. Could it be a minuscule gas leak from the spacecraft thrusters, giving them an unintended push? The math said no. Perhaps it was the gentle pressure of the spacecraft's own heat, radiating off and acting like a faint photon engine. Initial calculations could not account for it all. Maybe the gravity of unknown objects, like a hidden planet or a belt of distant rocks, was tugging on them. But no such massive structure was found. For years, this left a troubling gap. The anomaly suggested our understanding of gravity itself might be subtly wrong at the vast scales of the solar system, or that the spacecraft were drifting through a thin, unseen halo of dark matter. It was a classic space-time navigation puzzle where the map and the territory did not match. The mystery held until painstaking work went back to the simplest explanation: thermal radiation. By building a far more detailed model of how heat radiated from the spacecraft's nuclear power sources and bounced off their complex structures, engineers finally accounted for almost all of that phantom deceleration. It was a testament to human ingenuity, solving a riddle by looking more carefully at what we had already built. Yet its legacy is profound. For over 20 years, the Pioneer anomaly stood as a stark reminder that even in our own celestial backyard, the universe can present a bill for forces we do not fully understand. It taught us humility, showing that a discrepancy of less than a billionth of a gravity on Earth could captivate the world and challenge our models of reality. It proved that the greatest anomalies are often not grand cataclysms, but quiet, persistent whispers in the data. That solved mystery of drifting probes gives way to an even stranger one, a phenomenon that occurs not in the deep quiet, but in the dramatic slingshot maneuvers right past our own planet. When spacecraft like Galileo or Rosetta performed precision gravity assist flybys around Earth, stealing a fraction of our planet's momentum to fling themselves toward distant targets, something went subtly wrong. The meticulous tracking data revealed a tiny, unexpected bump. These spacecraft experienced velocity changes that our best models of gravity, both Newton's and Einstein's, could not fully explain. It became known as the flyby anomaly. The numbers were unequivocal. During its Earth flyby in 1990, the Galileo spacecraft gained about 4 millimeters per second more speed than predicted. Years later, the Rosetta Comet Chaser showed a discrepancy of nearly 2 millimeters per second. These amounts sound trivial, like a single grain of sand shifting on a vast scale, but in the hyper-precise world of orbital mechanics, they are glaring errors. A navigational miss by that margin over interplanetary distances could mean missing a planet entirely. So what was giving these spacecraft an unplanned push or an unseen break? One compelling idea points to a subtle effect predicted by Einstein's theory, frame dragging. Just as a spinning ball submerged in honey would twist the fluid around it, a massive rotating body like Earth is thought to gently drag the fabric of space-time around with it. Perhaps this twisted geometry imparts a tiny, unaccounted-for nudge to a passing spacecraft. Another possibility is more mundane but equally tricky: the faint whisper of Earth's atmosphere at extremely high altitudes. Even hundreds of kilometers up, where we consider space to begin, a few stray atoms remain. Could an uneven, unmodeled density of this thin exosphere create just enough drag or pressure to explain the speed change? Then there is the shape of Earth itself. Our planet is not a perfect sphere, it is a slightly squashed geoid bulging at the equator. Some physicists wonder if our gravitational models, which use an idealized smooth Earth, fail to capture the true complexity of this lumpy gravity field during a high-speed, close-in flyby. The flyby anomaly stands out because it is not a one-time fluke. It has shown up repeatedly, a consistent hiccup in our cosmic bookkeeping. It challenges our confidence in applying the grand laws of physics to specific high-stakes engineering problems. Each unexplained millimeter per second is a quiet testament that even around our own home world, with all our instruments watching, the universe still holds cards close to its chest. We plotted their courses with supreme confidence, only to watch them slip the grasp of our predictions by a hair's breadth, a hair that stretches across the solar system. But what if the entire universe has a hidden orientation, a cosmic north that should not exist? This brings us to the most profound and unsettling anomaly on our list, one written in the very first light of creation. To find it, we must look back over 13 billion years to a time when the universe was a searing hot plasma, just a newborn infant. As it expanded and cooled, that first light was finally set free, racing outward in all directions. Today, that ancient light reaches us as a faint, uniform glow bathing the entire cosmos, the cosmic microwave background. For decades, this cosmic afterglow has been our most powerful evidence for the Big Bang and our best map of the infant universe. We expected it to be almost perfectly smooth, a testament to the cosmological principle, the foundational idea that the universe is roughly the same in all directions and no place is special. But when satellites like Oumuamua and Planck mapped this radiation with exquisite precision, they found something that sent a chill through the world of cosmology. The map was not random. It showed strange, large-scale alignments, a pattern so statistically unlikely and so oddly oriented that scientists half-jokingly nicknamed it the axis of evil. The name is fitting, for this axis represents a direct challenge to one of our most sacred assumptions about reality. The anomalies within it are technical but staggering. First, there are the low quadrupole and octupole moments. In simple terms, these refer to specific patterns of hot and cold spots on the largest scales of the map. These patterns are much weaker than our theories predict, as if someone turned down the volume on the universe's biggest waves. More bizarrely, these faint patterns are aligned with each other and with our solar system's own plane of motion in a way that pure random chance says should be virtually impossible. It is as if the universe's largest structures are subtly pointing in a particular direction, a direction that, by sheer coincidence, seems to involve us. Then there is the infamous cold spot, a vast, unusually cold region in the southern sky, so large and so cold that it defies standard explanations. It could be a shadow cast by an immense cosmic void, a bruise from a collision with another universe bubble, or just a statistical freak of nature on a scale that is hard to comprehend? The implications are dizzying. If the axis of evil is real and not a fluke, it means the universe has a preferred direction. The cosmological principle, the bedrock of modern cosmology, would be cracked. It suggests that the seeds of the universe's structure were not perfectly random, but may have been imprinted by something that existed before the Big Bang, a pre-existing architecture we cannot see. Some theories even propose it could be a scar from our universe brushing against another in a vast multiverse, a permanent mark of a neighboring reality. Of course, the simplest explanation is that we are just incredibly unlucky, that we happen to live in a universe that, in our particular corner, looks strangely arranged. But the odds of that are astronomically low. The axis of evil forces us to confront a humbling possibility. We have always assumed we live in a typical, average place in a smooth, uniform cosmos. What if, instead, we are sitting in a location that is, for reasons we cannot fathom, genuinely special? The map of creation itself seems to be whispering that we are not looking at an anonymous universe, but one with a secret alignment, a hidden axis pointing toward a mystery we have only just begun to perceive. That unsettling sense of a special direction in the cosmos finds a terrifying echo in the motion of galaxies themselves. Hundreds of massive galaxy clusters are not just drifting apart with the expansion of the universe, they are streaming. They are all rushing together at incredible speeds toward a single, specific point on the celestial map, a point that lies far, far beyond the edge of everything we can see. This is the dark flow, and it is exactly what it sounds like, a mysterious current in the ocean of space-time for which we have no map. The discovery came from a brilliant piece of cosmic detective work using a phenomenon called the kinetic Sunyaev-Zeldovich effect. As the faint light from the Big Bang, the cosmic microwave background, passes through the hot gas of a galaxy cluster, it gets a subtle energy shift. By measuring this shift in hundreds of clusters, astronomers could essentially clock their speed relative to the universal background. What they found was staggering. These enormous structures, each containing thousands of galaxies, were all moving at over 2 million miles per hour in the same general direction. This is not random motion. It is a coordinated exodus, and the force behind it cannot be anything we know. The gravitational pull from all the visible matter and dark matter we have mapped in our universe is utterly insufficient to cause this. Even the repulsive force of dark energy, which drives the expansion of space, works evenly in all directions. It cannot create a one-way current, so what is pulling them? The most radical explanation is as simple as it is profound: gravity from something outside. The dark flow points toward a region of space so distant that its light has not had time to reach us in the nearly 14 billion years since the Big Bang. It is beyond our cosmic horizon, permanently invisible. Yet, if a truly immense concentration of mass exists there, a superstructure of staggering proportions, its gravitational influence could reach across the void and tug on everything in our neighborhood. Think of it like this: you are in a boat on a vast, calm lake, but you feel a steady, irresistible current pulling you. You look around and see no source for it on your lake. The only possibility is that somewhere over the horizon, beyond your view, lies a colossal waterfall, and its pull is drawing all the water and your boat with it toward its edge. The dark flow suggests our entire observable universe might be drifting toward a cosmic waterfall we cannot see. Some theorists take this even further, proposing the pull could come from the gravity of another universe entirely, a neighboring bubble in a vast multiverse brushing against our own. The idea is controversial, of course. Extraordinary claims require extraordinary evidence, and the signal is subtle, buried in incredibly complex data. Other scientists suggest it might be a systematic error in the measurements or an unaccounted-for local effect. But if it is real, the implications rewrite our place in the cosmos. It means our universe is not an isolated island. We are not merely expanding, we are also sailing, caught in a current set by geography we will never see, pulled by a source whose nature we can only guess. It transforms the universe from a self-contained system into a single room in an unimaginably larger mansion, with walls we cannot breach, but through which the faint vibrations of other structures can still be felt. The dark flow is not just an anomaly, it is a compass needle pointing directly at the greatest unknown of all, what lies beyond the edge of everything. This immense current points toward a specific region of space, a cosmic siren call we cannot ignore. Deep in the constellation Centaurus, something with the mass of tens of thousands of Milky Ways is pulling us, and everything in our galactic neighborhood, toward it at over 1,000,000 miles per hour. Astronomers call this unseen behemoth the Great Attractor. For decades, it was the ultimate cosmic blind spot because to see it, we had to look directly through the crowded, dusty plane of our own galaxy. This area is so choked with stars and cosmic debris that it blocks our view, creating what scientists call the zone of avoidance. It is like trying to spot a distant mountain range through a dense, permanent fog bank. We could feel its immense gravitational tug, mapping the peculiar velocities of galaxies as they streamed toward this point, but the source itself remained a shadow. Then, with infrared and radio telescopes that can peer through the dust, the picture began to clear, and it revealed something even more astonishing. The Great Attractor itself, a colossal concentration of galaxies known as the Norma cluster, was also moving. It was being pulled toward something else. That something is the Shapley supercluster, the single largest concentration of matter we have mapped in the observable universe, a staggering collection of galaxy clusters lying even farther away. This discovery sparked a profound debate. Is the Great Attractor a unique, overdense knot in the cosmic web, a destination in itself? Or is it merely a waypoint, a local ripple in the much larger cosmic river of the dark flow, with everything, including us, being swept toward Shapley and perhaps even beyond? The truth likely lies somewhere in between. Our local universe is caught in a complex hierarchy of gravitational pulls. The Milky Way, Andromeda, and dozens of smaller galaxies are bound together in our local group. Our entire group is falling toward the heart of the Virgo supercluster, and that entire supercluster, along with countless others, is accelerating toward the Great Attractor, which itself is a tributary flowing into the immense gravitational watershed of the Shapley supercluster. Visual maps of this motion are breathtaking, showing galaxies not as randomly scattered islands, but as leaves caught in a vast, slow-motion whirlpool, all spiraling toward hidden depths. The Great Attractor is no longer the ultimate mystery, but it remains a powerful symbol. It is a reminder that we are not still. We are passengers on a galaxy hurtling through space, caught in currents set in motion by structures we once could not see, pulled by gravity's invisible hand toward a destination we are only beginning to map. While the Great Attractor pulls on the fabric of our local universe, a different kind of signal once pierced the silence from a direction that held no massive structure at all. On August 15, 1977, at the Big Ear Radio Telescope in Ohio, a narrowband burst of radio waves slammed into the receiver. It lasted for 72 seconds, the exact duration a fixed telescope would observe a point source passing through its field of view. The signal was not random static. It was 30 times louder than the background noise of deep space, and it occupied a specific, eerily quiet frequency band that scientists had identified as a likely channel for interstellar communication, a channel shielded from the natural radio cacophony of the cosmos. When volunteer researcher Jerry Amon reviewed the computer printout days later, he saw the alphanumeric sequence that represented the signal's intensity, 6EQUJ5. He was so stunned by its perfect, unexpected profile that he circled it on the page and wrote a single, emphatic comment in the margin. Wow, that exclamation gave the signal its immortal name. What followed was decades of profound mystery. The Big Ear and every other telescope that ever listened pointed back toward that same spot in the constellation Sagittarius. They listened for a repeat, for a pattern, for any hint of a follow-up. The silence was absolute. The wow signal never returned. Explanations were proposed and meticulously tested. Could it have been a reflection from a passing man-made satellite? The frequency used and the signal's characteristics made that virtually impossible. Could it have been a natural cosmic event like a comet? Decades later, astronomers checked, but no known comets were in that precise region of the sky at that time. The signal's brevity and uniqueness became its defining, frustrating features. It was a cosmic shout that lasted just over a minute, followed by an eternal hush. Its legacy endures precisely because it fits the profile of an artificial, interstellar beacon so perfectly, while defying every attempt at a natural explanation. It stands alone as the best candidate we have ever recorded for a potential signal not of this world. Yet its fleeting nature speaks volumes about the scale of the anomaly we are dealing with. We are monitoring an ocean of space-time that is unimaginably vast and overwhelmingly silent. The wow signal is like hearing a single, clear, intelligible word shouted from a boat on that ocean. But by the time you turn your head, the boat is gone, lost in the fog, leaving you with nothing but the memory of the sound and the haunting question of who or what could have made it. It is a one-in-a-billion event that suggests something extraordinary can happen, but also that catching it again might require patience spanning centuries or luck we may never have again. That single, silent shout from the void is a whisper compared to the roar still echoing from the heart of our own galaxy. Towering above and below the Milky Way's bustling center are two colossal, ghostly structures, each one a blistering testament to a cataclysm we missed. They are the Fermi bubbles, and they are enormous. Picture two vast orbs, one north and one south of the galactic plane, each stretching 25,000 light-years from end to end. If you could see them in the night sky, they would cover half of it, dwarfing every constellation, but you cannot see them, at least not with your eyes. They are invisible in ordinary light, revealed only by their fierce glow in the most energetic form of radiation in the universe, gamma rays. The Fermi Gamma Ray Space Telescope mapped their faint, precise outlines, showing us a shape so clean and symmetrical it could only be the scar of a single titanic event. What could possibly create such structures? The prime suspect sits right at the coordinate of their origin, the supermassive black hole at our galaxy's core, Sagittarius, a star. While it is quiet now, astronomers theorize that several million years ago it might have awakened in a spectacular feast. As vast clouds of gas and dust spiraled into its gravitational maw, the black hole could have belched out twin jets of ultra-fast particles and radiation, blowing these gigantic bubbles out into the galactic halo like a cosmic smoke ring. The energy required is almost beyond comprehension, equivalent to hundreds of thousands of supernova explosions channeled into two opposing beams, but there is another plausible culprit. The galactic center is also a stellar nursery, a crowded, violent place where stars are born and die in rapid succession. Some scientists argue that not one black hole eruption, but a sustained frenzy of star formation could be to blame. A period of runaway stellar births would lead to countless massive stars living short, violent lives and exploding as supernova. The combined shock waves from all these simultaneous detonations could have blown a giant collective bubble, inflating it slowly over millions of years. The scale of the Fermi bubbles forces a humbling perspective. This was not a subtle event. It was a galactic-scale eruption that fundamentally reshaped the environment above and below our galaxy's disk, a storm that raged for millions of years. Yet here we are, living in the quiet aftermath. Our solar system orbits in the relatively peaceful galactic suburbs, and by the time the light from that eruption reached us, humanity was not even a species. We see the magnificent, lingering afterglow but have no memory of the explosion itself. It is a reminder that our galaxy has a violent, active history, and that the serene spiral we see in illustrations is just a snapshot in an album filled with cosmic violence. The bubbles are still there, slowly fading, a monument to a time when the heart of the Milky Way roared with a fury we can only now, millions of years later, begin to measure and wonder at. While the Fermi bubbles speak of a past galactic explosion, a single, unassuming star 1,200 light-years away began performing a strange dance of shadows that defied all logic. Known as KIC 8462852 or Tabby's star, this otherwise ordinary F-type star was caught by the Kepler Space Telescope doing something extraordinary. Its light did not dip in the gentle, rhythmic pattern of an orbiting planet. Instead, it plummeted in chaotic, asymmetrical plunges, sometimes by a staggering 22%. This was not a small shadow. It was as if something enormous and jagged was repeatedly drifting in front of the star, blocking a quarter of its light for days or weeks at a time. The immediate suspects were quickly ruled out. A planet, even a gas giant, could only cause a dip of about 1%. A swarm of comets, a popular early theory, could not explain the sheer depth and irregularity of the dimming without requiring an implausible number of them, thousands, all in a single, dense cluster. The debris from a catastrophic planetary collision would have left a telltale infrared glow of warm dust which was conspicuously absent. Each natural explanation hit a wall, leaving a glaring question mark hanging in the data. This is where the most famous and most speculative hypothesis emerged. Could the signal be artificial? Astronomers like Jason Wright proposed that an advanced civilization, a Type 2 on the Kardashev scale, might build a megastructure to harness their star's energy, a concept known as a Dyson sphere. A partially completed swarm of orbiting collectors would be vast, irregular, and could block exactly the kind of erratic, deep light patterns Kepler observed. The idea captured the public imagination, reinvigorating the serious scientific search for technosignatures, signs of technology beyond Earth. It is crucial to understand that most astronomers strongly favor natural, if exceedingly complex, astrophysical explanations. The leading candidate now is an uneven cloud of extraordinarily fine dust, perhaps from the disintegration of a moon or a family of asteroids, orbiting the star in a clumpy, dynamic ring. The star itself might also be prone to intense, hyperactive magnetic storms or internal processes that cause its brightness to fluctuate in ways we do not yet fully comprehend. Yet the anomaly's power lies in its stubborn refusal to be easily solved. Tabby's star became a cultural phenomenon, not because it is likely an alien megastructure, but because it is a perfect symbol of a genuine scientific frontier. It represents a moment where our catalogue of known natural phenomena came up short, forcing us to openly consider every possibility, no matter how extraordinary. It proved that the universe is still capable of presenting us with a light curve that makes even the most seasoned astronomers lean in, look at each other and sincerely ask what on Earth, or rather what out there, could possibly be doing that. The star continues to dim and brighten in its mysterious way, a silent beacon reminding us that some of the greatest discoveries begin not with an answer, but with a light that flickers in a way it simply should not. The mystery of a flickering star is one of patient observation, but some cosmic anomalies arrive as sudden, fleeting visitors. In October 2017, astronomers in Hawaii spotted a faint point of light moving at breathtaking speed. It was not on any predictable orbit within our solar system. This was Oumuamua, the first confirmed interstellar object ever detected passing through our celestial neighborhood. Its name, fittingly, means scout or messenger from the distant past in Hawaiian. The initial data was extraordinary. Its trajectory was hyperbolic, meaning it was not bound to the sun. It was just passing through on a one-way trip from another star system. Its speed and path confirmed it was a true interstellar traveler. But as telescopes tracked its departure, Oumuamua delivered its real surprise. After whipping around the Sun, as it should have been coasting away under gravity's influence alone, it exhibited a slight but definite non-gravitational acceleration. It was speeding up just a tiny bit, as if given an extra, invisible push. The most common explanation for such behavior in a comet is outgassing. As the Sun heats icy material, jets of gas erupt from the surface, acting like natural thrusters. The problem was, Oumuamua showed absolutely no signs of this activity, no surrounding cloud of gas or coma, no detectable tail of dust or debris streaming behind it. It was completely inert to our instruments, a dark, silent rock, yet something was accelerating it. This contradiction sparked intense debate. Some scientists proposed exotic natural explanations, like it being a shard of pure hydrogen ice that could sublimate without leaving a visible trace, or a dusty fractal aggregate so light that the pressure of sunlight itself could have given it a push. But the object's other peculiarities deepened the puzzle. Its brightness varied dramatically as it tumbled, suggesting an extremely elongated shape, perhaps like a cigar or a flat pancake, far more extreme than any asteroid or comet we have seen in our own system. This combination, the strange acceleration without a visible cause and the bizarre proportions, led Harvard astronomer Avi Loeb to propose a controversial hypothesis. He suggested that Oumuamua's profile was consistent with a light sail, a thin, manufactured object designed to be pushed by the radiation pressure of starlight. In this scenario, the acceleration was not from hidden gas, but from the faint but constant pressure of sunlight on a vast, thin surface. The scientific community largely remains skeptical, favoring natural origins that are strange but not alien. The debate, however, was less about proving aliens and more about highlighting a profound gap in our knowledge. Oumuamua was a test. It forced us to confront how little we understand about the formation and variety of objects in other star systems, and how poorly equipped we were to study an interstellar visitor that did not behave like a textbook comet. It passed through our solar system in a matter of weeks, a silent messenger carrying secrets we were not ready to decode, leaving us with only a fading point of light and a lingering question: what else is sailing the dark between the stars unnoticed? Oumuamua was a fleeting guest from the stars, but a far more patient and stunning geometric mystery has been holding its shape in our own solar system for decades. At Saturn's North Pole, a perfect hexagon of clouds spins in a slow, majestic dance. This is not a trick of the light or a fleeting storm. It is a persistent six-sided jet stream, a polygon etched into the atmosphere of a gas giant, first glimpsed by the Voyager probes in the 1980s and studied in exquisite detail by Cassini for over 13 years. The scale is humbling. Each side of the hexagon is wider than Earth's diameter, meaning two of our entire planets could fit side by side within this single, swirling feature. What makes it an anomaly is not just its existence, but its endurance. Earth's weather is chaotic and transient, with storms forming and dissipating in days. Saturn's hexagon, however, has maintained its precise geometric shape for at least 40 years, and likely much longer, through seasons that each last over 7 Earth years. It is a permanent fixture, a piece of cosmic architecture painted in clouds. In laboratory experiments, physicists can create similar hexagonal patterns by spinning a fluid, showing that such shapes can emerge naturally under the right conditions. But replicating the stability and perfect symmetry on the scale of a planetary atmosphere within the turbulent 1,000-mile-per-hour winds of a gas giant is another matter entirely. The leading theory involves standing wave patterns. Imagine the different bands of Saturn's atmosphere as layers of fluid moving at different speeds. Where these layers shear against each other, stable oscillations can form. The hexagon could be a colossal, six-petaled standing wave, a rhythmic vibration in the atmosphere made visible by clouds, much like a musical note creates a specific, unchanging pattern on a vibrating plate. This wave would be anchored deep within the planet, possibly tied to Saturn's rapid internal rotation or the unique conditions at its pole. Another idea suggests the shape is a self-organizing feature of turbulent flow, a stable vortex that just happens, against all odds, to have 6 sides due to the specific speed and density of Saturn's polar winds. Yet every explanation meets a wall of beautiful complexity. Why 6 sides? Why not 5 or 8? Why is it so sharply defined and so locked in place? The hexagon is a masterpiece of natural fluid dynamics, a demonstration that the universe can encode mathematical precision within the seeming chaos of a storm. It sits at Saturn's pole as a serene, rotating puzzle, a reminder that even within our own celestial neighborhood, worlds hold artworks we are still learning to see. It is not a sign of intelligence, but it feels like one, a perfect shape stamped on a planet by the invisible hand of physics, waiting for us to fully understand its language. From the serene geometry of Saturn's hexagon, we leap across the cosmos to a phenomenon of pure, violent energy. In the deep radio silence between galaxies, something screams. For just a few milliseconds, a point in the sky erupts with a flash of radio waves so powerful it outshines entire galaxies. This is a fast radio burst, and it is one of the most energetic and mysterious events in the universe. In that fleeting instant, it can release more energy than our Sun will produce over 80 years. The first one was discovered in archived data in 2007, a single, brilliant spike that seemed to come from nowhere. For years, each new detection was a one-off event, a cosmic flashbulb popping in the dark, leaving astronomers scrambling to understand what could possibly explode with such ferocity and then vanish without a trace. The mystery deepened with a crucial discovery. Some of them repeat. The most famous, known as FRB 121102, fires off multiple bursts in an unpredictable pattern, like a temperamental cosmic lighthouse. This repetition was a game-changer because it meant the source was not destroyed in the blast. It was something that could survive its own cataclysm again and again. Pinpointing the location of this repeater was a triumph of modern astronomy, tracing its origin back to a small, turbulent dwarf galaxy over 3 billion light-years away. Within that galaxy, the signal seemed to emanate from an environment of incredibly powerful magnetic fields, pointing squarely at a likely culprit, a magnetar. Magnetars are the ultramagnetic corpses of massive stars, neutron stars with magnetic fields 1,000 trillion times stronger than Earth's. A starquake on such an object, a sudden cracking of its rigid crust, could theoretically unleash the titanic energy of a fast radio burst in a single, focused beam. Then, in April 2020, the mystery came home. For the first time, a fast radio burst was detected originating within our own Milky Way, and it came from a known magnetar, SGR 1935+2154, which had just entered a period of intense X-ray activity. This was the smoking gun, the strongest evidence yet that at least some of these bursts are born from the apocalyptic physics of these magnetic monsters. Yet the case is not completely closed. The staggering variety in the bursts, some repeating, some not, some appearing oddly periodic, suggests there might be multiple cosmic engines at work. Could some be from the collision of ultra-dense objects like neutron stars, or perhaps from the violent birth of a black hole? There are even more speculative ideas on the fringe of science, like the possibility of beams from immense alien light sails, though most astronomers see natural explanations as far more likely. But beyond the question of their source lies their incredible potential. As these brief flashes race across the universe, they pass through clouds of ionized gas and the diffuse filaments of the cosmic web. This leaves a subtle fingerprint on the signal, a dispersion measure. By studying this, astronomers can use fast radio bursts as probes to weigh the invisible matter between galaxies, mapping the vast, unseen scaffolding of the cosmos. They are not just mysterious explosions, they are becoming tools, turning cosmic screams into a new form of astronomy that lets us see the unseeable. While some cosmic signals are brief and brilliant, others are a persistent, steady glow. Deep in the heart of our own Milky Way, the Fermi Gamma Ray Space Telescope has mapped a mysterious and enduring light. Centered on the galactic core is a diffuse, spherical haze of high-energy gamma rays, an emission that scientists call the galactic center excess. It is not a sharp point like a star, but a soft, pervasive fog of energy that blankets the inner region of our galaxy. And according to our best models, it should not be there in such abundance. The core of the Milky Way is a bustling, violent place, and we know of many things that produce gamma rays. There are pulsars, the spinning corpses of dead stars that beam radiation like cosmic lighthouses. There are also the constant interactions between cosmic rays, high-speed particles, and the dense clouds of gas that fill the region. Physicists have built sophisticated computer models to account for all of these known sources, but when they subtract that expected gamma ray light from the map Fermi actually sees, a significant surplus remains. This is the excess, a glow with no clear identification tag. This is where the mystery turns profound, because one of the leading hypotheses points to the most elusive substance in the cosmos, dark matter. The theory is elegant. If dark matter is made of weakly interacting massive particles, a leading candidate, then these particles could be their own antimatter counterparts. Where they are densely packed, like in the gravitational well at the galaxy's center, pairs of them might occasionally collide and annihilate each other in a flash of energy, producing the very gamma rays we detect. The observed shape and energy profile of the excess glow fits remarkably well with predictions for certain types of dark matter particle annihilations. It is a tantalizing possibility, a direct signal from the invisible 85% of the universe's matter, shining in a frequency we can finally see. Yet, extraordinary claims require extraordinary proof, and astrophysics offers a more conventional, though still fascinating, explanation. The glow could come from a vast, unseen population of millisecond pulsars. These are ancient neutron stars spun up to incredible speeds, orbiting in binary systems and emitting steady gamma radiation. They would be faint and numerous, like a swarm of fireflies in the galactic core, each one too dim for Fermi to pick out individually, but together creating the exact same diffuse haze. Distinguishing between these two possibilities, a dark matter signal or a pulsar swarm, is one of the great detective challenges in modern science. It is like trying to decide if a distant, uniform hum is coming from a single, mysterious engine or from 10,000 tiny, buzzing insects. The answer lies in the fine details of the gamma ray map, looking for subtle clumping that would betray the presence of point sources or a perfect smoothness that would favor dark matter. For now, the galactic center excess remains a luminous question mark at the heart of our home galaxy, a siren song that could be the whisper of dark matter itself, or the collective murmur of stellar corpses we have yet to count. That persistent glow at the galaxy's heart is a question about our cosmic ingredients, but a far more urgent crisis is unfolding across the entire observable universe. At the very foundation of modern cosmology, two of our most trusted measuring sticks are telling us two different stories about reality. This is the Hubble tension, and it is not a small discrepancy. It is a full-blown emergency in our understanding of the cosmos. The Hubble constant is the number that tells us how fast the universe is expanding right now. It is the ultimate speedometer for the fabric of space itself. For decades, we have honed two brilliant, independent ways to measure it. The first method looks back to the dawn of time, to the afterglow of the Big Bang, the cosmic microwave background. By studying the tiny temperature fluctuations in this ancient light, the Planck satellite could calculate the ingredients of the infant universe, the amounts of dark matter, dark energy, and ordinary matter. Plugging those numbers into our standard model of cosmology, known as lambda CDM, gives us a prediction for what the expansion rate should be today. This is the early universe measurement, and it is exquisitely precise. The second method works in our own cosmic neighborhood, the late universe. Astronomers use cosmic lighthouses called Cepheid variable stars. These stars pulse with a rhythm that is directly tied to their true brightness. By measuring their pulse rate from Earth, we know their intrinsic brightness. Then, by seeing how dim they appear in distant galaxies, we can calculate precise distances. Combine these distances with the redshift of those same galaxies, which tells us how fast they are receding, and you get a direct local measurement of the expansion rate. This work, championed by teams using the Hubble Space Telescope, is also incredibly precise. Here is the problem. These two numbers do not agree. The local late universe measurement says the cosmos is expanding about 10% faster than the early universe data predicts. 10% might not sound like much, but in the world of precision cosmology, where error bars are tiny, it is a gigantic universe-shaking gap. It is the difference between two world-class archers, each claiming to be perfectly accurate, yet one consistently hitting the bullseye while the other's arrow lands firmly in the next ring over. Every conceivable check has been run. Teams have searched relentlessly for hidden systematic errors, some subtle miscalibration in the distance ladder, some overlooked effect in the ancient light. The discrepancy stubbornly remains. This tension suggests our beautiful, elegant standard model, lambda CDM, might be incomplete. It is as if we have a perfect recipe for a cake that has worked for every test batch, but when we finally bake the real thing, it rises to a slightly different height. Something is missing from the list of ingredients. Theorists are now racing to propose what that new cosmic component could be. Perhaps dark energy, the force driving the expansion, is not constant but has evolved over time, growing stronger or changing its nature in a way we did not anticipate. Maybe dark matter has properties we have not yet imagined, allowing it to interact with itself or with light in novel ways. There could even be unknown types of relativistic particles, like ghostly neutrinos with strange masses, that flooded the early universe and altered its expansion history. Each potential fix is thrilling, for it points to new physics beyond our current understanding. The Hubble tension is more than a technical disagreement. It is a direct challenge, a crack in the foundation of our cosmic worldview. It tells us that either we have made a collective, subtle error in measurement on a monumental scale, or the universe is fundamentally more complex and wondrous than our best model allows. The answer, when it comes, will not just give us a number. It will force us to rewrite the story of everything. This expansion crisis shakes our fundamental laws, but a different kind of law was seemingly challenged right here on Earth inside a laboratory. The story of the M drive reads like science fiction. Imagine a rocket engine that needs no fuel, no fiery plume of expelled propellant, just a sealed, tapered metal cavity pumped full of microwaves. According to its proponents, this simple device could generate a tiny, persistent thrust, nudging a spacecraft forward without pushing anything backward. It promised to overturn one of physics' most sacred principles, Newton's third law, that for every action there is an equal and opposite reaction. You cannot push against nothing, yet the M drive claimed to do exactly that. The proposed mechanism was exotic, suggesting the microwaves bouncing around the asymmetric cavity could create a pressure difference, effectively pushing harder on one end than the other. Teams around the world, including a small, advanced propulsion group at NASA called EagleWorks, built their own versions and reported the impossible, minute but measurable thrust signals, often just a few dozen micronewtons, the weight of a single sesame seed. For a moment, it felt like a revolution. Headlines proclaimed the dawn of a warp drive, a thruster that could harness the fabric of space-time itself, promising trips to Mars in weeks. The cultural impact was immense, capturing the public's longing for a shortcut to the stars. Yet, within the broader scientific community, the reaction was deep and profound skepticism. Physicists were not just doubtful, they were puzzled. The reported thrust violated the conservation of momentum, a cornerstone of physics that has held true from billiard balls to galaxy clusters. The overwhelming consensus pointed not to new physics, but to old, stubborn problems, experimental error. The forces measured were so incredibly small that they sat right at the noise floor of the instruments. Could they be from thermal expansion? As the cavity heated from the microwaves, parts of the test apparatus might have expanded minutely, mimicking a thrust. What about the subtle push from the Earth's magnetic field interacting with power cables in the lab, or even the gentle atmospheric currents in a vacuum chamber that was not perfectly empty? One by one, more rigorous tests sought to eliminate these errors. A team in Germany built an ultra-sensitive balance in a near-perfect vacuum and found that when they accounted for all known effects, the thrust signal vanished. It appeared the sesame seed weight of thrust was a mirage, a collective measurement ghost. So why does this debunked idea belong on a list of genuine anomalies? Because the M-drive controversy represents a critical, self-correcting process of science at its most frustrating and beautiful. It was a meme for hope that crashed against the wall of experimental rigor. The years spent chasing, testing, and ultimately disproving it were not wasted. They pushed engineers to develop more sensitive measurement techniques, to consider subtler sources of error, and to reaffirm why those fundamental laws are so trusted. They withstand our most desperate attempts to break them. The M-drive is a monument not to a breakthrough but to a rigorous process, a reminder that sometimes the most exciting signal is the one that forces us to clean up our lab, check our cables, and look even harder at the empty space we think we understand. That rigorous process of checking our cables in the lab was taken to the ultimate laboratory in 1996, high above the Earth. The Space Shuttle Columbia carried a revolutionary experiment, a satellite tethered to it by a 12-mile-long, thin, conducting cable. The idea was elegantly simple. As this enormous tether cut through Earth's magnetic field at orbital velocity, it should act like a giant dynamo, generating an electrical voltage along its length. Standard electromagnetic theory predicted a potential of about 3,500 volts. What happened next was not simple at all. When astronauts deployed the satellite, the tether did not just generate electricity, it roared to life. The voltage soared to an astonishing 3,500 volts as predicted, but the current that began to flow was a shock. Instead of the expected half an amp, the system pulled in over 1 amp, a discrepancy of more than double the predicted power. In some phases of the experiment, current levels were an order of magnitude higher than any model had foreseen. This was the tethered satellite anomaly, a classic case where a beautifully clean theory met the messy, complex reality of space. The tether was not moving through a perfect vacuum, but through the ionosphere, a thin plasma of charged particles. Scientists quickly realized their models had vastly underestimated how efficiently the tether would collect electrons from this environment. Think of the original prediction as expecting a light drizzle to fill a rain barrel. What actually happened was more like positioning that barrel under a waterfall. The conductive tether, charged to a high positive voltage by the dynamo effect, became an irresistible attractor for the sea of free electrons in the plasma around it. But the sheer scale of the electron collection suggested something even stranger was at play. One leading theory involves the formation of a complex plasma sheath, an enhanced cloud of charged particles that ballooned around the tether's collecting end. This sheath could have acted as a gigantic, invisible funnel, vastly increasing the effective area for electron collection far beyond the tether's mere physical cross-section. Other physicists looked to more exotic possibilities. Could there have been unexpected wave-particle interactions in the plasma, a kind of resonance that supercharged the electron flow? On the furthest edges of speculation, a few wondered if the moving tether was interacting not just with the planetary magnetic field, but with the properties of space-time itself in a way not described by classical electromagnetism. While that remains highly speculative, the core lesson was immediate and practical. The tethered satellite Anomaly proved that generating power in space is not just theoretically possible, it might be far more efficient than we dreamed. The experiment, though it ended prematurely when the tether snapped, was a dazzling and unintended success. It revealed a hidden richness in the near-Earth environment, showing that the emptiness of space is actually a dynamic sea of energy waiting to be tapped. For future engineers dreaming of orbital power stations or electrodynamic tethers for spacecraft propulsion, the anomaly is not a failure of theory but a beacon. It points to a future where we might not just travel through space but truly plug into it, drawing energy directly from the planet's magnetic embrace. The promise of drawing energy from space itself speaks to a universe filled with invisible power, but that power sometimes arrives in forms so extreme they challenge the very laws that govern reality. This brings us to one of the most violent and puzzling deliveries the cosmos can make, the ultra-high energy cosmic ray. In the 1960s, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin calculated a fundamental speed limit for these atomic nuclei screaming across the universe. Their reasoning was brilliant and simple. The cosmos is not empty, it is filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation. Imagine a marathon runner trying to sprint through a dense, persistent mist. Every droplet they hit slows them down, saps their energy. For a proton or atomic nucleus traveling at nearly the speed of light, that mist is this sea of ancient photons. According to the GZK limit, any cosmic ray particle with an energy above about 5 times 10 to the 19th electron volts should, within a relatively short cosmic distance, collide with these background photons. In a process akin to hitting a brick wall, that collision would rob the particle of its colossal energy, breaking it down long before it could ever reach Earth. This established a theoretical horizon, a distance beyond which such ultra-high energy particles simply could not travel to us. It was a clean, elegant prediction. And then we started catching them. In October 1991, an observatory in Utah detected a single particle that shattered all expectations. It carried an energy of about 300 electron volts. To put that in human terms, this single subatomic particle, likely a proton, hit our atmosphere with the kinetic energy of a well-thrown baseball. Scientists, in a fit of understated awe, named it the "Oh my God" particle. Its energy was so far beyond the GZK limit that it seemed impossible. Where did it come from? If the GZK calculation is correct, such a particle could only have originated within our own local galactic neighborhood, a mere stone's throw away in cosmic terms, perhaps within 150 million light-years. Yet when astronomers scour that region of space, they find no suitable cosmic engine, no nearby quasar, no active galactic nucleus, no supernova remnant powerful enough to accelerate a particle to such a mind-bending speed. This is the heart of the GZK cutoff problem. We are detecting particles that by all rights should not exist. They have either traveled too far or they come from nowhere we can see. The implications force us to question our understanding on multiple fronts. One possibility is that our maps of nearby space are incomplete, and there is a monstrous, hidden accelerator practically in our backyard, a source we have somehow overlooked. Another, more unsettling idea is that our knowledge of particle physics at these extreme energies is flawed. The equations describing how these particles interact with the cosmic background might change at energies we cannot replicate in any earthly collider. But the most profound possibility touches the foundation of Einstein's relativity. The theory relies on Lorentz invariance, the principle that the laws of physics are the same for all observers, regardless of their constant velocity. Some speculative theories of quantum gravity suggest that at these insane energies, space-time itself might have a granular, foamy structure. A particle surfing this quantum foam might experience a slight alteration in its fundamental properties, a violation of Lorentz invariance that could allow it to travel farther without losing its punch. In essence, the oh my god particle and its kin could be the first experimental hints of quantum gravity, a tiny crack in the smooth continuum of relativity, showing us that at the highest energies, the universe plays by rules we are only beginning to dream of. Each one that strikes our atmosphere is a messenger from an unknown frontier, carrying not just immense energy, but a direct challenge to our picture of how space, time, and matter behave at the very edge of the possible. These cosmic messengers challenge the very fabric of physics, but sometimes the universe offers a spectacle that is less a challenge and more a breathtaking work of art. In January 2002, a faint, anonymous star in the constellation Monoceros did something no one had ever seen before. Over a series of weeks, the star now known as V838 Monocerotis did not explode. Instead, it swelled. Its outer atmosphere expanded at a staggering speed, inflating to a diameter larger than the orbit of Jupiter, causing its brightness to increase by a factor of 10,000. For a brief, glorious moment, it became one of the brightest stars in our entire galaxy, shining with a cool, red luminosity. This was a luminous red nova, a stellar event so rare and peculiar it defied the standard script of stellar death. The real magic, however, unfolded in the years that followed, as observed by the Hubble Space Telescope. The star's sudden flash of light began racing outward through space, illuminating vast, pre-existing shells of dust that had been ejected from the star in earlier, quieter epochs. As this light pulse struck successive dust clouds, they lit up like a series of cosmic lanterns, creating an expanding halo of glowing rings around the central star. This phenomenon, called a light echo, provided a stunning, three-dimensional movie of the event, a celestial ripple moving through the dusty halls of space. The beauty of the light echo was matched by the depth of the mystery. What could cause a star to brighten so cataclysmically without destroying itself? The leading theory points to a violent merger, a stellar tango that ended in a dramatic embrace. One scenario suggests two main sequence stars, like our Sun, spiraling into each other over time until their cores finally collided, releasing a titanic wave of energy that blew the outer layers into a vast, cool envelope. Another possibility is that a giant planet, many times the mass of Jupiter, plunged into its host star, transferring immense energy and triggering the Great Inflation. The precise physics of this merger, however, remains elusive. How does the energy transfer through the star? Why does it produce such a distinctive red glow and such a specific pattern of expansion? The event was a one-time laboratory, a chance to observe the violent choreography of stellar fusion and gravity in a way no simulation could perfectly predict. V838 Monocerotis stands as a beautiful anomaly, a reminder that the cosmos is not just a place of fundamental forces and dark mysteries, but also a gallery of transient, magnificent phenomena. It showed us that a star's final act can be a slow, radiant inflation instead of a violent detonation, painting the darkness with echoes of its own history for all to see. The luminous echoes of a stellar merger show us the universe's capacity for beauty, but its earliest moments were governed by a far more rigid kind of chemistry. In the first 20 minutes after the Big Bang, the entire cosmos was a nuclear fusion reactor, forging the universe's first atomic nuclei from a searing soup of protons and neutrons. This process, Big Bang nucleosynthesis, created the primordial ingredients for everything to come. The theoretical calculations for this cosmic alchemy are astonishingly precise, predicting exactly how much of each light element should have been cooked in that initial furnace. For the two most abundant products, hydrogen and helium, the predictions match the observed abundances in the oldest stars and gas clouds almost perfectly. It is a triumphant confirmation of our model for the universe's first moments. But for the third lightest element, lithium, the math fails spectacularly. The universe holds only about 1/3 of the lithium-7 that our equations insist should exist. This is the cosmic lithium problem, and it is not a minor accounting error. It is a fundamental mismatch between the recipe we have written for creation and the ingredients we actually find in the cosmic pantry. Think of it as a cosmic baking experiment. We have a perfect, time-tested recipe for a cake based on the precise laws of physics. We follow it to the letter, and when we pull the cake from the oven, the amounts of flour and sugar are exactly right, but we are missing 2/3 of the chocolate chips. The chocolate chips are lithium, so where did they go? One possibility is that our inventory of the modern universe is wrong. Perhaps lithium is being destroyed inside stars far more efficiently than our stellar models predict. As stars churn and mix their interiors, fragile lithium nuclei could be dragged down into hotter regions and broken apart by nuclear reactions long before the star dies and returns material to space. This would mean the oldest stars we observe, which should preserve the primordial lithium abundance, have actually been slowly destroying it for billions of years, hiding the true initial amount from us. Another avenue points to gaps in our nuclear physics knowledge. The first 20 minutes were a frenzy of particle collisions. Could there be unknown or poorly measured nuclear reaction pathways that produced less lithium-7 in the first place, or that converted it into other elements like beryllium or helium more quickly? Physicists have scrutinized the nuclear cross-sections, the probabilities of these ancient reactions, but the discrepancy stubbornly remains. The most thrilling possibility is that the problem is not with stars or nuclear data, but with the physics of the infant universe itself. What if the fundamental constants, like the strength of the nuclear force or the number of types of neutrinos, were slightly different during those first critical minutes? A tiny variation could shift the entire nuclear equilibrium, producing less lithium. Or perhaps exotic, undiscovered particles from the dawn of time decayed in those first moments, releasing energy that altered the temperature and density of the nuclear soup just enough to skew the results. The lithium shortage could be a fossil, a chemical fingerprint left by physics that operated only in the universe's first breath. This is not just a problem for astrophysicists, it is a fundamental chemistry problem on the scale of all existence. Lithium is a key piece in the periodic table's origin story. Its anomalous absence forces us to question whether we truly understand the nuclear furnace that set the stage for every star, planet, and molecule that would follow. It is a quiet but persistent signal from the universe's first 20 minutes, whispering that our recipe for everything, while brilliantly successful, might still be missing a line or two of instruction. The cosmic lithium problem is a chemical whisper from the first moments of time, but some of the deepest anomalies are not found in ancient stars, but written in the theoretical fabric of reality itself. Our two most successful theories, quantum mechanics and general relativity, describe the universe with breathtaking accuracy, yet they refuse to speak the same language. At their violent intersection, where gravity is strong and scales are tiny, the equations break down, producing paradoxes that feel like the universe contradicting itself. Two of the most famous predictions from this troubled marriage are Hawking radiation and the Unruh effect. Both are stunning consequences of quantum field theory in curved space-time, and both suggest that our notion of empty space is an illusion. Hawking radiation tells us black holes are not truly black. Due to quantum fluctuations at the very edge of the event horizon, pairs of virtual particles can pop into existence. Normally, they would annihilate each other in an instant, but if one falls into the black hole while the other escapes, the escaped particle becomes real, carrying away a tiny bit of the black hole's mass. Over eons, this process causes the black hole to evaporate. The Unruh effect, meanwhile, states that an observer accelerating through what seems like empty space will not see a vacuum. Instead, they will feel themselves immersed in a warm bath of particles. From their perspective, the vacuum is not empty at all, it is full of thermal radiation. This is not a mechanical effect from friction, but a fundamental feature of quantum fields for someone undergoing acceleration. For decades, these two ideas were celebrated as brilliant, consistent pillars of theoretical physics. Then, physicists looked closer and realized they might be fundamentally at odds. The conflict crystallized in the black hole firewall paradox. Imagine an astronaut falling toward a black hole's event horizon. According to Einstein's principle of equivalence, which is the foundation of general relativity, the astronaut should feel nothing special as they cross that invisible boundary. Space-time should feel smooth, but if we apply the rules of quantum mechanics meticulously, particularly the requirement that information cannot be truly destroyed, a different and terrifying picture emerges. To preserve information, the quantum fields at the horizon must be highly energetic, entangled in a specific way. This intense entanglement, when combined with the predictions of Unruh radiation for the accelerating observer, suggests that the event horizon would not be a smooth gateway. It would be a searing wall of ultra-high energy particles, a literal firewall that would incinerate the astronaut instantly. This is the paradox. General relativity says the horizon is uneventful, a place of no return but no drama. Quantum mechanics, when pushed to preserve its sacred rules, says it must be a place of violent, destructive energy. Both cannot be true. The firewall paradox is more than a technical disagreement. It is a screaming signal that our current framework for combining gravity and quantum theory is incomplete or even wrong in extreme conditions. Resolving it is not about choosing one theory over the other. It is about finding a new language, a theory of quantum gravity, that makes both the smooth space-time of Einstein and the informational rules of quantum mechanics emerge from a deeper, unified picture. This could involve radical ideas like space-time being composed of discrete loops or two-dimensional holograms, or the very concept of an event horizon needing revision. The Unruh and Hawking discrepancy is an anomaly of pure thought, a crack in the theoretical bedrock. It shows us that sometimes the most profound mysteries are not out in the distant cosmos, but hidden in the equations we use to describe it, waiting for a genius to rewrite the rules and show us what space-time truly is. Theoretical paradoxes exist in the equations, but a true cosmic void stares back at us from the constellation Boötes. This is not a simple empty patch of space. The Boötes void is a staggering spherical chasm, a bubble of near-nothingness roughly 330 million light-years across. To grasp its scale, if you placed our Milky Way at its center, the nearest edge of this emptiness would still be over 65 million light-years away. In a universe we believe is built on a vast, interconnected cosmic web of galaxies strung along dense filaments, the Boötes void is a gaping hole in the tapestry. Where we would expect to find thousands, perhaps even tens of thousands of galaxies, surveys have catalogued only a few dozen lonely island universes drifting in that immense dark. It is not completely empty, but its sparseness is profoundly unsettling. This is not how matter should be distributed if the seeds of structure were spread evenly after the Big Bang. How did a region this vast end up so deserted? One possibility is simply a statistical fluke, a natural and rare underdensity in an otherwise uniform distribution. Think of it as a colossal bubble in the foam of the universe, an air pocket that just happened to form on a mind-bending scale. In an infinite cosmos, even the most improbable structures must appear somewhere. Yet the sheer size of the Boötes void pushes against the limits of what our standard models of cosmic evolution can comfortably produce. It challenges the idea that gravity alone, acting on dark matter, could have cleared out such an enormous volume so completely and left it so barren for so long. This has led scientists to consider more exotic origins. Could it be the scar of a phase transition in the very early universe, a moment when the fabric of reality shifted and left behind a permanent defect, a bubble of different physical laws that repelled matter? Or perhaps it is a region where dark energy, the force accelerating cosmic expansion, took a different form or strength, a phenomenon theorists call quintessence, pushing galaxies apart with unusual ferocity long ago. When we visualize the cosmic web, we see brilliant knots and luminous filaments. The Boötes void is the profound shadow between them, a negative space that defines the structure as much as the light does. Its existence forces a humbling question. Are we, in our galaxy-rich neighborhood, the typical inhabitants of the cosmos, or are we the exceptional ones, living in an overdense suburb while most of the universe is a far emptier, lonelier place than we ever imagined? That profound emptiness in Boötes is defined by the brilliant structures around it. But what if those structures themselves share a secret alignment? Across the universe, the most luminous beacons known to science are sending us a coordinated signal. These are quasars, the dazzling cores of distant galaxies, powered by supermassive black holes feasting on surrounding matter. As this material spirals into the abyss, it forms a blazing, spinning disk and often shoots out twin jets of energy perpendicular to that disk. The axis of this spin, the rotation axis of the entire system, is a fundamental fingerprint of the black hole's behavior. For decades, we assumed these axes would point in random directions, scattered chaotically across the sky like countless tops spun by different hands. The universe, after all, should have no preferred direction. Yet, when astronomers began to analyze the light from thousands of quasars separated by billions of light years, they found something that defied that assumption. The rotation axes of these quasars are not random. Over truly staggering, incomprehensible distances, they appear to be aligned with each other, and even more shockingly, aligned with the vast filamentary structures of the cosmic web in which they sit. This correlation spans scales so large that these quasars have never been in causal contact since the beginning of time. Their light has only just reached us, meaning they could not have communicated or influenced each other to arrange themselves in this way. It is as if you walked into an art gallery on another continent and found every painting hung at precisely the same slight angle as the ones in your hometown museum, despite the curators never having met. This discovery strikes directly at the heart of the cosmological principle, the foundational idea that the universe is homogeneous and isotropic, the same in all directions when viewed on a large enough scale. A preferred alignment of cosmic structures on such a grand stage suggests the universe might have a grain, like wood, a subtle directional preference woven into its very fabric from the start. So how could such an alignment be imprinted? One compelling idea points to the influence of primordial magnetic fields. In the universe's first moments, before even the first stars flickered on, titanic magnetic fields may have stretched across the infant cosmos. These fields could have acted like cosmic guides, influencing the collapse of the first clouds of gas and dark matter that would eventually form galaxies and their central black holes, imparting a preferred spin direction to the entire process. Another, even more profound possibility lies in the epoch of cosmic inflation, that fraction of a second when the universe expanded faster than light. The quantum fluctuations that were blown up to cosmic size during inflation, which became the seeds for all galaxies, might not have been perfectly random. They could have carried a slight polarization, a directional bias that was then frozen into the large-scale structure of space-time as it expanded. This would mean the initial conditions of our universe, the very first settings at the moment of creation, had a kind of spin already written into them. The alignment of quasar axes is not a violent anomaly, but a quiet, geometric one. It suggests that the universe's largest structures might remember a common origin, a shared instruction set from a time before time. When we look at those brilliant, distant quasars, we are not just seeing isolated engines of destruction. We might be seeing the echoes of a cosmic symmetry, a hidden pattern left over from the first instance of everything, a pattern that gives the expanding cosmos a subtle, coherent spin we are only now beginning to read. The subtle alignments of quasars point to a hidden structure in the cosmos, but that structure itself seems to be missing something vital. Our cosmic inventory has a major discrepancy. When we tally up all the ordinary matter we can see, the stars, galaxies, glowing gas, and interstellar dust, we come up short, drastically short. According to the precise recipe of Big Bang nucleosynthesis, the universe should contain a specific amount of this normal, or baryonic, matter, the protons and neutrons that make up everything from planets to people. Yet our census of the present-day universe finds only about half of what that primordial chemistry says should exist. This is the missing baryon problem, and for decades it was a glaring hole in our understanding of where all the stuff in the cosmos actually went. It was not dark matter, that is a separate, even larger mystery. This was about the ordinary atoms we are made of, simply vanishing from the ledger. So where did half the universe's normal matter go? The answer lies not in the bright cities of stars, but in the dark, vast countryside between them. Astronomers now believe the missing baryons are hiding in the diffuse filaments of the cosmic web, the immense scaffolding that connects galaxy clusters across the universe. This intergalactic medium is not completely empty. It is filled with a tenuous, superheated gas, warmed to millions of degrees by the gravitational energy of the universe's large-scale structure. This gas is so hot it does not glow in visible light. It emits only faint X-rays, making it incredibly difficult to detect directly. Finding it became a cosmic detective story, requiring ingenious methods to see the invisible. The first clue came from looking at the brilliant light of distant quasars. As that light travels billions of light years to reach us, it passes through these faint, hot filaments. Atoms within the gas, like oxygen and hydrogen, absorb very specific wavelengths of the quasar's light, leaving a unique fingerprint in its spectrum. By studying the patterns of these absorption lines, astronomers can map the otherwise invisible gas, tracing its distribution and temperature along the line of sight. It is like using a distant lighthouse to study the fog bank in front of it. The second method uses a phenomenon called the Sunyaev-Zeldovich effect. As the ancient light from the cosmic microwave background passes through a galaxy cluster, it interacts with the hot electrons in the cluster's gas. These electrons give the photons a tiny energy boost, leaving a subtle, specific shadow or distortion in the microwave background map. By carefully analyzing these distortions, scientists can weigh the hot gas not just in the dense clusters, but in the fainter filaments stretching between them. This technique acts like a cosmic scale, measuring the mass of the hidden hot plasma. The evidence from both methods is now overwhelming. The missing baryons have been found. They are not missing at all, they are just extremely elusive, spread out in a vast, hot ocean that fills the spaces between the islands of galaxies. This discovery closes a major chapter in cosmology, finally reconciling the universe's ancient chemical recipe with its modern content. It tells us that the ordinary matter of the cosmos is not primarily in the stars, but in the spaces between them, a diffuse, superheated reservoir that contains more atoms than all the galaxies combined. We live in a universe where the most common form of familiar matter is an invisible million-degree gas, a hidden sea in which the glittering galaxies are merely rare and beautiful islands. That hidden sea of ordinary matter exists within the geometry we think we know. But what if that geometry can be flipped, creating a mirror image of our most terrifying cosmic objects? Black holes dominate our imagination, regions of space-time where gravity is so intense that nothing, not even light, can escape. They are the ultimate cosmic sinks. But Einstein's equations of general relativity are, in a mathematical sense, time-symmetric. They work just as well running forward as they do backward. And if you mathematically reverse the flow of time for a black hole, you get its bizarre theoretical twin, a white hole. This is not a place of crushing gravity, but of ultimate expulsion. A white hole is a region of space-time that cannot be entered from the outside. It is a cosmic fountain, a one-way exit door from which matter and energy can only pour out, but nothing can ever get in. If you tried to approach one, you would find space-time itself pushing you away, accelerating you outward as if you were caught in an irresistible, universal repulsion. While black holes are thought to form from the collapse of massive stars, white holes, if they exist, would have to be born differently. They are not something that could form from normal astrophysical processes we see today. Instead, they are considered primordial, perhaps artifacts of the universe's violent birth. This leads to a stunning speculation. Some theorists have proposed that the Big Bang itself could be viewed as a white hole event, a singular eruption of all space, time, and matter from a point of infinite density. Our entire observable universe, in this view, would be the interior of a white hole, forever expanding outward from that initial explosive exit. The hypothesis also offers a tantalizing, if highly speculative, solution to the ultimate fate of a black hole. Stephen Hawking's work showed that black holes should slowly evaporate over eons through quantum effects. But what happens to all the information that fell in? The white hole idea suggests a radical possibility. Perhaps when a black hole evaporates completely, it does not vanish. Instead, it might undergo a quantum transition, rebounding as a white hole, spewing out all the information it ever consumed in a final, radiant burst. This could solve the infamous black hole information paradox. So, if white holes are popping into existence or have always been there, could we ever see one? Astronomers look to the most violent, transient events in the sky for clues. Some have wondered if the mysterious fast radio bursts, those millisecond flashes of immense radio energy, could be signatures of microscopic white holes blinking into and out of existence. Even more powerfully, the most energetic gamma-ray bursts, which outshine entire galaxies, have been considered candidates. A white hole erupting into our universe would release a cataclysmic amount of energy in a very short time, matching the profile of these incredible explosions. Yet, for all its mathematical elegance, the white hole remains a profound anomaly, an edge case. Most physicists consider them physically improbable, if not impossible, in our stable universe. They require exotic conditions that violate the usual flow of cause and effect, essentially demanding that a singular event in the future, the eruption, dictates conditions in the past. They sit at the very boundary of what general relativity allows and what physics as we understand it can tolerate. They are less a prediction and more a reminder of the strange, unvisited corners of Einstein's universe, places where time runs backward and fountains of creation replace pits of oblivion, showing us that even our most established theories contain doorways to realities we can scarcely imagine. Einstein himself called it spooky action at a distance, a phrase that captures the deep unease surrounding our next anomaly. It begins with a thought experiment from 1935, devised by Albert Einstein, Boris Podolsky, and Nathan Rosen. They sought to expose what they saw as a fatal flaw in the then new theory of quantum mechanics. Their paradox, known as EPR, hinges on a bizarre property called quantum entanglement. Imagine you create two particles together, perhaps two photons, in such a way that their quantum states are linked or entangled. You then separate them, sending one to a laboratory on Earth and the other to a detector on Mars. According to quantum mechanics, until you measure a property of one particle, like its spin or polarization, both particles exist in a fuzzy superposition of all possible states. The moment you measure the particle on Earth and find it spinning up, the particle on Mars instantly and with absolute certainty becomes spinning down. This correlation happens faster than light could travel between them. To Einstein, this was impossible. It suggested information was traveling instantaneously, violating his own theory of relativity's cosmic speed limit. He believed there must be hidden variables, unseen factors determined at the moment of entanglement that would explain the correlation without any spooky communication. For decades, this was a philosophical debate, a clash of interpretations about the nature of reality. Then, in the 1960s, physicist John Bell provided a way to test it. Bell's theorem created a mathematical inequality. If local hidden variables were real, if everything was set at the moment of separation, then certain statistical results of measurements would stay within a specific bound. If quantum mechanics was correct with its inherent spookiness, the results would violate that bound. When experiments were finally performed with enough precision, the answer was clear and shocking. The quantum predictions won. Entangled particles do influence each other instantaneously across vast distances. This is not a flaw in the experiments, it is a feature of the universe. The anomaly here is not in the data, but in our conceptual map of space-time itself. We are forced to accept that the universe is non-local, that two things can be connected in a way that transcends the classical distance between them. It is as if the fabric of reality has threads that do not run through space, but underneath it, tying things together in a hidden landscape. This forces us into strange interpretations. Perhaps every measurement splits reality into parallel worlds, as the many worlds theory suggests, and the correlation is just a record of which branch you are on. Or maybe particles are guided by pilot waves in a higher dimensional reality, as in de Broglie-Bohm theory, where influences can be non-local. The most profound implication is the direct conflict with general relativity, which paints a smooth, local picture of space-time where nothing travels faster than light. Quantum mechanics, with its proven non-locality, suggests information somehow bypasses that structure entirely, reconciling these two visions, creating a theory of quantum gravity that can accommodate spooky action, is the single greatest challenge in modern physics. It means our understanding of space itself, the stage upon which every other cosmic anomaly plays out, is fundamentally incomplete. The universe is not just stranger than we imagine, but in this case, it operates by a logic that seems to ignore the distances we see, connecting points across the cosmos with a whisper that travels no distance at all. That spooky, non-local connection defies our sense of distance, but the final anomaly on our list threatens something even more fundamental, the arrow of time itself. It emerges not from quantum puzzles, but from the pristine mathematics of Einstein's own equations. When physicist Roy Kerr solved these equations for a rotating black hole in 1963, he found something far stranger than the simple, point-like singularity of a static black hole. Inside a spinning black hole, the crushing gravitational endpoint is not a point but a ring. This Kerr singularity is a loop of infinite density, a one-dimensional rip in the fabric of space-time. And this shape changes everything about the interior. According to the Kerr solution, if you were to somehow survive the journey past the event horizon of a rotating black hole, you would not necessarily be crushed at the center. The ring singularity's unique geometry creates a bizarre inner landscape. Mathematical pathways known as closed time-like curves appear to open up around the ring. These are not just paths through space, they are loops in time itself. In a region containing a closed time-like curve, an object could travel on a trajectory that brings it back to its own past. It is a mathematical blueprint for a time machine built into the heart of our most successful theory of gravity. The implications are as dizzying as they are disturbing. Such a possibility shatters our everyday understanding of cause and effect. Imagine using such a curve to travel back in time and prevent your own grandfather from meeting your grandmother. If you succeeded, you would never be born, which means you could never have traveled back to stop the meeting, which means you would be born after all. This is the classic grandfather paradox, a logical contradiction that seems to make time travel into the past an impossibility. The universe, it seems, cannot tolerate such nonsense. This is why most physicists believe closed time-like curves, while mathematically allowed in the pure Kerr solution, are physically forbidden in reality. The great theorist Stephen Hawking proposed a chronology protection conjecture, a kind of cosmic law that prevents time travel to the past. He suggested that the very act of trying to create a time machine, of twisting space-time into such a knot, would trigger catastrophic feedback. Quantum effects would become infinitely strong, creating an impenetrable wall of energy, a firewall of a different sort that destroys the time loop before it can be used. In essence, the laws of quantum gravity, which we do not yet fully understand, would likely step in to enforce causality, to keep the timeline consistent and paradox-free. Yet the sheer fact that our best description of gravity mathematically permits such curves is a profound anomaly. It tells us that the fabric of reality, as described by general relativity, is malleable enough to be bent into a loop where future and past connect. The Kerr solution is not science fiction, it is a rigorous prediction. It forces us to confront the fact that our deepest theory of space and time does not inherently contain an arrow. The direction of time, the feeling that the past is fixed and the future is open, may not be woven into the fundamental geometry of the cosmos. Instead, it might emerge from something else, perhaps from the statistical behavior of countless particles, or from the still unknown rules of quantum gravity that overrule Einstein's equations in the most extreme regimes. The ring singularity and its closed time-like curves represent the ultimate frontier of this mystery. They are a ghost in the machine of reality, a whisper from the equations that says the universe could, in principle, be threaded like a needle through its own history. That this ghost is almost certainly banished by laws we have yet to write does not diminish its power. It stands as the final, stark reminder that when we push our understanding of space and time to the absolute limit, we find not solid ground but a labyrinth of possibilities where even the sequence of events becomes a question waiting for an answer. From the theoretical labyrinth of closed time-like curves, we emerge with a new map of the cosmos, one etched not in certainty, but in glorious, unresolved questions. Our journey through 25 unexplained anomalies has taken us from the quiet drift of the pioneer probes in our own backyard to the screaming geometry of Saturn's hexagon, from the silent shout of the wow signal to the universe-spanning crisis of the Hubble tension. We have witnessed stars that flicker without reason, voids of staggering emptiness, and galaxies caught in a current flowing toward an unseen horizon. Each of these cosmic glitches, whether a fleeting visitor like Oumuamua or a permanent fixture like the axis of evil, serves the same vital purpose. They are the universe's way of poking holes in our textbooks. A discrepancy of a few millimeters per second in a spacecraft flyby, a shortage of lithium in ancient starlight, a pattern in the first light of creation that points in a preferred direction. These are not failures of science. They are its fuel. Every anomaly, even those eventually solved like the pioneer deceleration, began by highlighting the limits of our current models, forcing us to look closer, think deeper, and question our most comfortable assumptions. They prove that discovery does not begin with an answer, but with a stubborn piece of data that simply will not fit. This relentless, collective detective work is how we inch closer to truth, building a better, weirder picture of reality with each mystery we confront. The true wonder revealed by these 25 puzzles is not that we have everything figured out, but that we so clearly do not. The cosmos is far stranger, more dynamic, and more ingeniously bizarre than our everyday experience could ever suggest. It is a place where empty space seethes with quantum potential, where geometry is etched into clouds on a planetary scale, and where the fundamental arrows of time and causality are not guaranteed, but constantly probed by the mathematics of extreme gravity. This ongoing conversation between human curiosity and cosmic mystery is the greatest story ever told. So we turn the question to you after this voyage to the edges of understanding. Which anomaly reshaped your view of the universe the most? Was it the chilling coordination of the dark flow, the beautiful frustration of Tabby's star, or the profound simplicity of the lithium problem? Share your thoughts in the comments below. We are endlessly fascinated by these discussions. If you crave more deep dives into the strange and beautiful corners of reality, be sure to subscribe. For now, keep looking up. The cosmos is not a settled fact, but an invitation, a grand and mysterious puzzle waiting for its next